In this circuit, we're going to have a thick bulb and a thin bulb wired in parallel, which is different from my previous video where they were wired in series. And we'll see that quite a few things are going to change in this situation, but some things will still be the same. Just like my previous video, we've got a 2-volt battery. Okay, so we can start off just by labeling our equipotentials. We're going to have the positive 2-volt equipotential right here on the positive terminal. We'll have the 0-volt equipotential on the negative terminal. And let's see, we've got a 1 ohm bulb and a 3 ohm bulb. And based on what I did in my previous videos, hopefully it's clear that, this one is the higher resistance path. So this thin bulb, I'll call it R2, that's the 3 ohm bulb. And the thicker one has less resistance to current, so that'll be the 1 ohm bulb. All right, now interestingly, they have the same lengths, so that's something that they'll have in common. So we assume that the differences in resistance is just due to their cross-sectional areas being different. Okay. Now we want to draw the surface charge that's created in this situation. So when we're in contact with the positive terminal of the battery, we just want a lot of surface charge there. And how you choose to show that is up to you. But we need a gradient whenever we're dealing with current flow. And the more gradient there is, like this, the bigger the change in surface charge, the stronger the field will be. Now, I actually don't want the gradient to change a whole lot in this section. And we said that any point that was in contact with the positive terminal, like through a conducting wire, all the points on that wire would be at approximately the same potential. So that means we've got 2 volts at both these points. So that's important. We got about 2 volts there, and we're going to have about 0 volts over here. All right, so let me just draw more surface charge here. We want a lot of it because this is our highest potential. But I do want it to, I want the pluses to be a little bit more spread out, because somehow we have to create that field. We have to create that push that pushes the charges through the circuit. So I'm trying to spread them out a little bit more than they are up here. Okay, so that's one way to do it. Now let's create our field. Our field goes from positive to negative, so we just want a very weak field here. Okay. And I'll do the same thing over here on the negative side as well. All right, that looks pretty good there. Let's draw in the field as well. Okay, and these are field vectors. All right, now I'm not going to draw the field inside the conductors leading to the bulbs just yet. Okay, but one thing I can do is I can draw the field inside the bulbs themselves. Now, in order to reason out what the field should be like at those locations, we might want to think back to the past, and there was a formula for field. One of its expressions looked like this. Delta V equals E delta X. But if we rearrange that, we see that the field is the potential difference divided by the distance. And so that tells us something about what the fields should be like in these bulbs. When they were in series, if you remember, let me just to refresh your memory, when they were in series and we had the thick bulb wired directly to the thin bulb, I said that the field would be stronger in one of these cases. I said that because the thin bulb had more resistance, there would be a stronger field in it compared to this thicker bulb. That was for series though. Okay. We said that there would be a drop of 1.5 volts across that thin bulb and a drop of 0.5 volts here. But what do you notice about the potential drops across the bulbs now? It's different. We're at 2 volts at this point and 0 volts at that point. And here we've got 2 volts and then 0 volts on the other side of the bulb. So you see the delta X's and the voltage drops are the same. So that helps us reason out what the field strengths must be like inside those bulbs. So it must be that they're actually equal. And I can express that with just one long arrow of equal length for both bulbs. Okay. Now, let's draw our equipotentials. Now, the equipotentials are based on position and field. So, since we have a nice constant field in these bulbs, that means that our equipotentials are going to be the same for both bulbs. Okay? So we're going to have the 1 volt here. We'll have, let's see, I'll mark every half of a volt. So we'll have 0.5 volts there. And then we'll have 1.5 volts there. And those will actually be all the equipotentials that I need for this problem. Okay. Next question says, how does the flow rate of charge compare in the 2 bulbs? Okay. So one thing we might do is we might think about formulas we have for flow rate of charge, right? So here's one. According to Ohm's law, if we do I equals delta V over R, this can tell us about the currents in those branches, right? So I'm going to do it for both bulbs. We'll do it for I1, for resistor 1, and then we'll also do it for I2. All right, so let's see, I1 for the thick bulb is going to be 2 volts over 1 ohm. So it looks like we're going to get 2 amps in there. So let me write that down. 2 amps in this section. Now let's do it for the thin bulb. 2/3 of an amp. Okay. And let's write that in as well. So interestingly, one difference between series and parallel is that the branches of parallel can have different currents in them. Okay. With series, we always had the same current. I said it was 0.5 amps everywhere when we solved that circuit. Okay. But this time, we don't have that. And also, what about the power? I said that the power that was dissipated by the first bulb was 0.25 watts in my video. But over here, the power dissipated by the next bulb was 0.75 watts. And that was expected to make the thin bulb much brighter than the thick bulb. But let's find out what would happen here. How would the brightnesses of these bulbs compare? So first, we got the potential difference across both the bulbs. They're the same. Now we can use the voltage and the current to find the power. And this is a little bit of a new formula. The power is found by multiplying the potential difference times the current. And that tells us about the brightness of the bulbs. Assuming that they're similarly constructed bulbs of similar materials and all that. All things being equal, the more power, the brighter the bulb. So let's multiply for bulb 1, which had a 2-volt drop, and it has a current of 2 amps. That would give us a power of 4 watts. Now let's find the power of bulb 2. Two-volt drop, but a small current. Now we've got only 1.3 watts, it looks like. So in this particular setup, interestingly, the thick bulb dissipates much more power than the thin bulb, so it's going to be much brighter. Okay, so now that we have that down, we could also look at the currents inside the branches and see how they'd be related to the field strength. That's a little trickier to do. One of the formulas we have for relating current and field would be, we have I equals NQA times the drift speed. And then we also have that the field strength is equal to the resistivity times the current density. So with that in mind, if we just take a look at these conductors, say point A versus point B, we know the currents are very different in them. So we're going to assume that N stays the same material. Q stays the same, and let's assume that they're wires of equal diameter. Okay. So if that's the case, then for A, when the current goes up, then interestingly, the drift speed in that section is going to go up as well. And if we were to rearrange and divide by A, we would get this I over A equals N times Q times the drift speed. Okay. And I over A, as I mentioned in one of my videos, is called J, the current density. Okay. So clearly, if the current goes up and the drift speed goes up, then the current density goes up too. And now, if we look back at our other formula, assuming that the resistivity of the material stays the same because it's the same metal that we're going through here, then as the current density goes up, the electric field goes up too. So that's why I didn't really want to draw the electric field inside those sections just yet, because there's a difference between them. So I know that the current density in A is higher. It's the higher current, the higher current density, and the higher electric field as well in that branch versus this one. These things are all proportional to each other. But how does A and B compare to, say, point C? Let's say it has the same thickness and the same material and all that. How will the field strength there compare to A and B? It's a valid question. And the answer comes from a thing called Kirchhoffs' junction rule. Kirchhoffs' junction rule. What Kirchhoffs' junction rule says is that the sum of currents coming into a particular junction has to equal the sum of the currents that leave that junction. And this is important for parallel circuits because the current that we have coming in through, from the positive terminal here is going to split. It's going to split into two parts, where some of the current is going to go through the middle branch and some of it's going to go through the lower branch. So what we want to do to figure out how much current is going through point C is we can actually add the two currents that we had found. Current at point C is not going to be the same as the two of them. It's going to be the sum of them, 2.67 amps. Okay, and the idea is that electrons have to decide, are they going to take this path or are they going to continue and take the other path? But we have to have conservation of charge, which means charges can't be created nor destroyed. So at these junctions, they have that decision to make of which way they're going to go. Now, if they choose the wider path, you could think about it like a river. There'll be more of them flowing through at a faster rate because we have a larger current. But if they take this path, they're actually going to just go really slow because there's more resistance in this path, So anyway, the answer to this should have been that the field strength here has to be pretty large, like almost as big as it is at C, because it's 2 amps there, 2.67 amps here. But the current at B is small, and the field is small there as well. Hope that makes sense. What we'll do next is we will analyze the circuit symbolically. We'll create a circuit diagram for it. All right, so let me go over to here. Let's create our setup symbolically. We have 2 bulbs wired in parallel this time. we've got a 2-volt battery. All right, so we can label different points around the circuit, what their voltage is. That's helpful. We would be at 2 volts here, 2 volts here, 0 volts there, 0 volts there. There's another one of Kirchhoffs' laws. It's called Kirchhoffs' loop law or loop rule. What the loop rule says is that whenever you're going from positive to negative all the way around a circuit, in any one loop, you have to drop the entire voltage of the battery. Basically, the rule says that the sum of all the changes in potential in a closed loop is equal to 0. So we gain potential when going through the battery. Okay? So there's a plus 2 volts there. Okay, when we go through that part. Then we have to lose 2 volts in our light bulb. And then we come back to 0. So the same rule holds, though, for this loop. All right, so that's just a very simple introduction to Kirchhoffs' loop rule. We'll actually do much more with it in the future. But right now, we're just showing how we've got 2 parallel paths. And in both of those paths, the sum of the delta V's have to add to 0. So that's another way that I can tell that we're going to drop 2 volts in each bulb. All right, anyway, what we'd really like to do, though, is simplify this into one resistor, just like we did with the capacitors. So take the 2 bulbs, combine them into just one resistor here, which we'll call it our EQ. All right, now the rule for resistors in parallel is different from what it is for resistors in series. I said before that the resistors in series would have an equivalent resistance of R1 plus R2. But this is not series, this is parallel. So the equivalent resistance when we're in parallel is given by this formula. 1 over R1 plus 1 over R2. It's the reverse of what it is for capacitors. When capacitors were in parallel, we just added their capacitances, and the result had more capacitance than any one of them individually. But with light bulbs, interestingly, the resistance of 2 bulbs in parallel is less overall than any one of them alone. The reasoning for this is that the electrons, when they go through the path, they have more ways to get to the other side. Okay, like there's more cross-sectional area in total if you were to, say, combine the bulbs. More bulbs in parallel is actually better for the electrons if they want to get to the other side. Anyway, let's plug in the numbers. It's going to be 1 over, we said that the top one was 1 ohm. And the bottom one was 3 ohms. So we'll have that. All right, our REQ comes out to 0.75 ohms. As you can see, it is less than either of the 2 bulbs was alone. All right, our next job is to figure out how much current will be traveling in our equivalent circuit. So we want to find the current through Req. To do that, I'll just use Ohm's law. The total voltage drop in this single element circuit here would just be the whole battery's voltage, 2 volts. And now we have the new equivalent resistance, so plug that in. It comes out to 2.67 amps as expected. That's what we had found on the other page right here. So let's write that this branch has an I through the battery. That's the amount of current going through the battery of 2.67 amps. And it's the same on this side too. Okay, but now we have to figure out how much goes through bulb 1, how much goes through bulb 2. The calculation that's required, I had actually already done. All it is we just want to apply Ohm's law to just this bulb alone now. All right, so that's easy to do. We'll find I1 by I1 equals delta V1 over R1, 2 volt drop, 1 ohm resistor, 2 amps. So this is 2 amps. Then we can find I2. I2 is delta V2 over R2, 2 volts over 3 ohms, 0.67 amps. And now we've solved everything about the circuit.